Okay, I started. I think it's working. It did not actually work last week. Um, so tested it. Seems to work. So hopefully it's going to work. It worked on my, so it should work for this one. All right. So chapter 6, book the lecture, and I put up a place to turn in chapter 6's homework assignment. Now, one of the things that you'll see is that I put a link to the PDF of the assignment right here, but all of the you can hear me on the coast, right?
You can't really see the kind of video.
Okay. I'm all blurry. What I was about to say here, and then I'll see if I can be less blurry, is that all are under files. So they're all there. Even if the assignment hasn't been created in so if you wanted to work in it ahead. I just actually got that question, but he stepped out. All right. Oh yeah. It's like up and it's way zoomed in. It's even like tilted a little bit. That's funny. That's as far as it actually goes. Hey, one thing I just mentioned is all the assignments. If you hit files, they're all. I haven't created an assignment for every single one. If I'm ever behind again, or if you ever want to work ahead, they're in there. They're looks blurry now. It auto focuses. So probably the reason why I was like pointed right in a weird place that it couldn't auto. You know. Okay. Great. So we're all set. Today we're going to discuss continuous probability distributions and probability mapping. So we're going to discuss. Like last week. It's not a very long chapter. I prepared a few more examples this week for us to go through. So hopefully we'll be able to spend the time with those because there's not a whole lot of the material. This is a pretty interesting topic, and again, we'll kind of build on material that we need to talk about later in the course. I'm just going to stay with this view so I can go in and out, go to different things, even though it's got the slides over here. All right. I don't know. I don't think we talked about a random variable, the concept of a random variable yet, but let's just say we had a number like variable, so we gave it a letter like we do with most variables, x. And with x represented a value, and every time we observed x, x could change. It's stochastic, in other words, not always the same. And we could assign a value based on a distribution. In other words, x could represent any number, any real number, so it could have a decimal place, in a distribution. And if it was a uniform distribution, like we talked about last week, the probability of getting any number would be equal. And we could have all sorts of uniform distributions, but sometimes we standardize our distributions. And so we could say that we're going to restrict our uniform number, our random number, to a number between 0 and 1. And that means that we would have an equal probability of drawing between 0 and 1. We could also say that a random number variable represented a different distribution. We talked about a few different last week, and most of those distributions were discrete. In other words, getting real, not real, we're only getting integers. 1s, 2s, 3s, those things. Well, today we're going to continuous probability, specifically one particular distribution, because this one distribution, the normal distribution, has a lot of different things in nature follow a distribution. And interestingly, even those things that don't have a random distribution, when we sample them, in other words, when we say, okay, I'm gonna pick a number from this distribution at random, oftentimes the number that we pick, that number is normal distribution. So anyway, move on to the next slide here. This is a picture of the normal distribution. What it looks like. Okay. Like all distributions, we can describe by its mean. Okay, that's a measure of central tendency that we talked about earlier, back in week 2. We talked about measuring a distribution in terms of its and its kurtosis. So the kurtosis is how pointy the distribution is. The skewedness is how much of a tail in one direction versus another. So if it has more of a tail in the direction, it's got positive skewedness, negative direction, negative skewedness. Distribution actually has a of 0. Okay? It's not skewed at all. So when we're measuring skewedness, we're actually measuring the difference from the normal distribution. All right. So lots of things are normally distributed. They all have different means, and they all have different standard deviations, right? But what makes them all normal? A normal distribution is one that follows these characteristics. In other words, if x we're measuring, if we can say that it's a normal variable, if random variable where we have the value of x equal to the mean and the expected value of the expected standard deviation equal to the standard deviation. I mean, the value of the standard deviation is the variance squared. A random variable that looks like this. Okay? In other words, if we can standardize it, then it's a normal distribution. We can standardize it using this formula. X is the value in question. So if we're trying to figure out let's just start with light. Okay. So if we got a bunch of people and we're measuring their heights, we can figure out how different their value is. That's what x represents here. By subtracting the mean and dividing it by the the standard deviation. This is the notation for standard deviation. That would be the variance. Dividing it by the variance, or the standard deviation. Okay. What this does is this term is a standard deviation, and this is basically the difference between any particular value and the mean. Score is telling us how different an observation is from the in a standardized fashion, in a standard fashion, because they're the same for the mean and the standard deviation. So using this, we come up with a number, and that number is actually in standard deviations. The z-score, the value of the z-score, units are standard deviations. So a z-score of 1, that we have a that observation is 1 standard deviation away from the mean. Score of 2 means that observation is 2 standard deviations away from the mean. Okay. And so on. The value of 1.5 means 1.5 from the mean. So what that means is, if we're talking about height and we find an observation, we plug it in the z-value of 1, or if we're talking about like the weight of turtles, and we weigh a bunch of turtles over the years, okay? And we look at one particular observation, and we to the mean and divide it by the standard deviation. And we also find out that value is 1. Then that turtle is just as from its population as that height is from its population. And the reason that this is neat is that standard deviation follows this. The normal distribution has these characteristics. If something is 1 standard deviation, that means that that it is that there are, well, okay, this is the cumulative function. This is the cumulative distribution for the normal distribution, the cumulative distribution function for the normal distribution. And so the area under the curve is what's shown here. Okay. So on either side of 1 standard deviation, you got roughly 68%. Another way to think about this is, let's say we're looking at that turtle that we weighed. It was 1 standard deviation above the mean. I didn't into that formula. Well, we can see that in the population, there was 34.1 plus 34.13, which we know is 68.23, plus 30.59 plus 0.282. So if we add all those values up, we would get an Excel table. Yep, right here. So if we add all these up right here, I meant to say if we add all these up with our little turtle, we could say that turtle is heavier than about 84% of the population. Okay, but that's the thing. So that turtle is not an average. It's about 84% heavier. Or another way to think about it is that we could talk about this probabilities and say like if we went out and weighed it and it was at a z-score of 1, look at this side and say the probability of pulling a turtle out of the population that weighs this much or more would be this side of the standard curve, which would be roughly 1%, because 0.84 minus 1 is 1/6. So the probability of getting a turtle that weighed this much or would be that much. Or we could look at it the other way. Getting a turtle that weighed this much or less is 84%. So we can talk about these areas as probabilities. I mean, that's what they are. So here's a different application of the same principle. So if we had a distribution of annual precipitation, in other words, how much precipitation does Washington, D.C. get? Well, the average is that it gets 39.95 inches. That's the average. The standard deviation isn't shown here, but we can actually calculate that because we've got some. We've this at 1.07 standard deviation. So the standard deviation is almost 48. So what we've done here is we plugged 48 into here, 0.95 into here, and divided by whatever the standard deviation is, not shown on this chart. And we get a z-score of 1.07. The z-score of 1.07 tells us that, the probability of exceeding 48 in any year is about 14%. So that's how we read that, the area under the curve. Say the probability of getting less than 48 inches in a year. Anybody? Probability of getting less than 48 inches in a year. If we know what this is.
It's 1.
Yeah, it's 1 minus that, exactly. So the probability of getting less than 48 inches of rain in any given year is 1 minus that, which is pretty good. So if you live in Washington, D.C., 88 given year, you'll have about 85%, 86, 85, 85.7 percent, 85.8% chance of getting that much rain or less. Yeah. If you're trying to get more than 48, this is the number. So you're saying in a given year, the probability of getting more than inches of rain is that number right there.
Oh, okay. You don't have
Nope. But trying to figure out what the probability of getting the mean and 48%. Right here. Okay. Let's say we didn't know that. We can actually figure out, even if all we know is this, we can figure out that. Okay? Anybody have a formula for doing that?
0.5. What is that?
Yeah, so the area under half of the curve is also always 0.5. Figure out any area under the curve with just the 10. So here, the amount of precipitation exceeding 9 years out of in Washington, D.C. So just looking at a different portion of the curve. Now, this works. So not all normal distributions look exactly the same. Normal distributions have than others. You can have a normal distribution with any given mean and any given standard deviation. The mean doesn't restrict the standard deviation. So here's an example of two different distributions with the exact with the different standard deviations, and we could still calculate under the curve. But once they're standardized, they all look like this. Right? They're standardized. Their z-score looks like this. The distribution of their z-scores, but their distribution themselves, of the actual values, may look different. All right, so we got this recipe for assessing probability based on a normal distribution. So we got a normal distribution. Lots of things are normally distributed. In fact, we'll learn later that we can assume that there are many many variables follow this distribution. So this is the recipe that we go through to calculate the probability. The first thing we do is calculate the standard score. So we use the formula. To do this, we do need to know two pieces of information. R on there is the mean. We need to know that. And S is the standard deviation. It's ideal to know the population standard deviation, but that's not possible. Rarely. And so the sample deviation is an acceptable alternative, particularly when a lot of samples. By a lot, at least 30 usually. Okay. We'll learn about the t-distribution later. T-distribution is also a distribution, but it can deal with different size samples. So that's the. Then we take any particular observation to that formula, and we come up with a z-score. Now, to do that, the next step is to determine the probability from the table. But to determine the probability from the table, we need to look at the question and look at what the table reports. Sometimes they're different. Okay? So, almost all tables come with a little diagram like this, and they show you a black-in area. The one in your book, it's at the very end. It's on page 303 of your book. That one is interesting. I should have put that one's interesting because it actually reports this area here in your book, the one to that area. When I took a statistics class, it reported this area. Okay. But I've seen these report different areas under the curve. They each report a different area. And the question is asking about a different thing. Like, sometimes your question the probability of exceeding this value, the probability of that value being lower than a certain value, and then the probability of a value falling to two different values. So those are really the three types of questions that get asked a lot. So one of those. So the final step is to evaluate the probability value. So probability you're seeking to find, is it exceeding, is it less than? Okay. And that may involve finding a different value than the table. And remember, the total area in the curve is 1, and that the half of the curve is 0.5. Let's do a few examples here. So we have this is an example. Okay, this is the calculation of heating degree days exceeding 1 year out of 10 in Lexington, Kentucky. We have there's an explanation of what a heating degree day is, but basically is an estimate of 1 heating degree day is like the amount of energy it takes to heat a home for 1 day. So under some standard condition. So in some areas, there's a lot more heating degree days than others because they're colder areas. So for Lexington, Kentucky, what they've done is they've used past data to figure out what the average heating day value is. And they figured out that it's 4695. So deviation using past data was 370. So information, let's say we had heating degree days required by, so we had all that data. We could calculate the mean and the standard deviation. Pretty easy. We just add up all the numbers, divide them by the number, values, and we get the mean, and we use the mean to calculate the standard deviation. We've practiced this. Okay, so what if we want to ask the question, what is the probability in any given year that the heating degree day, actually this question's, sorry, what value should we expect to see 90% of the time? What value will only be exceeded approximately once every 10 years? Okay? That's what we're asking. So we're actually asking the opposite question that I talked about up here. So what we're trying to do is figure out what the value will be if P is 10. Okay? So we can use the table to determine. So let's look at the table here. So the p-value, the area under the curve, is 0.10, which is just off both the table in your book and the z-value chart here. Okay. So we're looking at the probabilities. That's these values right here. These are the z-values. So we're looking for 0.10. 0.10. The closest value we can get to is right there. 0.1003. And so the way we is 1.28. See how 8? We could also, if you have your book, you can go to and find points in this table, but they are all points. So 0.1. Oh, and look. So in the book, you'll notice we're trying to find this value. So we don't want 0.1. What value do we want to look at in the table? If we're trying to find this area, here I'll go back to. So we're trying to find this area, but the table in the book is actually this area. 0.4, exactly. It's telling you. Okay. So we look for the thing that's closest to 0. Anybody tell me what that number is? Look for 400 somewhere in the table. Closest value is 1.28. Where's 4.28? Did you say 1.28? Yeah. Okay. So how did you get that? Well, the value in the table to 4.000 is 3.97. You guys see that? And that's 1.28. Is that a positive value? And this Z table reported a negative value. Well, it's because this is reported value on this side. See, so it's negative. And this one in your table is reporting positive. But since it's a symmetrical distribution, since it's a symmetrical distribution, take that value, 1.28, even if it was negative, and figure out that it's being true on this side. Okay? So it's 1.28. Now we can take that value, 1.28, we can solve for x. So you've got x over here. The way you could do the algebra there and say x equal to the mean was this value, z, which was the 1.28, and the standard deviation, which was that value. So we multiply these two together and then add 4.5, and we come up with a value. So that is 5168. So what is another way to say, why did we figure out that value? That's what this sentence is. Lexington will exceed 5,168.60 1 year out of 10. You can actually ask questions from both directions. We could say, I've got a probability and I want to find out what the critical value is. That's what that's called, the critical value. Or I've got a value and I want to find out how unusual it is or what the probability of pulling out this sort of thing is. Let's say I went fishing and I caught a really, really big fish. Well, if I knew what the average fish was for that and the standard, I can figure out just how unusual it is. Of course, it's hard to get that information. So that's the standard normal ability. Let's try another one here. Okay, this is also an example from your book. This is the second example here. The one that is the average last day of frost. So, this is actually something that farmers care about. What's the probability that if I go out and plant crops, that my crops won't encounter any more frost? So, that's the type of question I'm answering here. To do this, days are actually it's hard to subtract. I mean, you could do it. May 31st from April 11th, right? But it's easier and easier to use them in statistics if we convert days to the days since January 1st. And we call this the. So a Julian date for March 17th, for example, is 7. In other words, it's the 76th day of the year. The 90th day in the year is March 31st. April 91st day of the year. Step would be to calculate Julian days, and then mean and the standard deviation using Julian days. So the way you would read is that the average last day of frost for this area is almost the 76th day, which is. However, the standard deviation of those frosts is about 15 and a half days in either direction. So 15 and a half days in either direction is the 91st day. Well, in just the positive direction. This is 15 and a half. Okay, so this step 2 is if I want to know, okay, I'm on April 1st. If I'm going to plan on April 1st, I want to know what the probability of encountering a freeze after the 1st will be. Well, I can calculate the z-score by all these numbers into the formula, and I get a value of 0.97, which I told you is very close to 1. And what does 1 mean? What does the z-score mean?
Standard deviation.
Exactly. It's very close to 1 standard deviation. We already established that, but we're just feeding it in to verify it. It's very close to 1 standard deviation. We want this value to be very close to that value I Excel before, which was 0.8413, the inverse of that, 1.8. It's going to be close to that, but let's use the table to figure it out. Well, if we have a z-score of 7, we go 0.97. That in your table, you get a value of 3340, the one in the book. This is showing right here. The way you read the table is looking for a z-score, you go down till you see the number closest, which is 0.9, and then you go over to 7, and we get 334, which is 0.3340. That's that value. To actually get this value, we have to do some subtraction. In order to get this value right here, we have to do we have to take 0.5. We get 0.1660. That's the Waycross, Georgia. Waycross, Georgia. So 1660. That's the value there. That's the area under the curve, and it is really close to what we'd expect from 1 standard deviation. If we're on a table, like let's say you have a different table to deal with, you'd read it 0.9 is right there, and we would get 1660, which is the same value as we got there. We didn't have to do the subtraction. So depending on what z-table you're using, you'll have to, the way I got that, 0.97. It's hard to see, that says 1660. Should I do it on here so it's on the video? So 0.97, 1660. That's already the answer we need. We don't need to do any subtraction. Technically, it's opposite, like it's this area and we want that area, but all right. So what we're saying is if we're planting something and it absolutely cannot tolerate a frost, then a 16% chance of it failing on frost. Now, if it could like tolerate a frost, but we're going to have some extra money to handle the field differently, to cover everything, then we can plan for the cost and work that in our costs over time. We know that 16 times out of every 100 years, we're going to have to spend this cost, or there's a 16% chance that we'll have to take these measures to make sure that our crops don't freeze. Those are some different applications for that example. Okay. So here are a couple of other examples. Other examples don't give the mean or the standard deviation. We're just looking, we're just asking the question, just to kind of drive home the point. The question, what is what is the z difference what's the probability where the z is between 0 and 0.45? Remember, 0 is what? A z value of 0 means, what's the z value of 1? So a z value of 0 is another word for the mean, exactly. This is asking, what's the probability that z falls between 0 and 0.5? So would we expect this to be a pretty high? I mean, it's in the kind of the meat, right? It's in this section, 0.5. We're looking at some pretty large number. I mean, everything's less than 1. It's all relative. So let's look at the answer there for A. So here we're looking, if we look at the table, go to, we know that the 50, we don't even have to look at the table for that. That's why this says 50. But let's look at the table for 5. Okay? This table doesn't even have it. And neither does this table. Usually you're more concerned with tails. Okay, so maybe that was a bad example, but I did get the value of a different table. And so looking at that value, you get a value of 17%. So 17% of the time, we're going to get something that is between 0 and less than half of a standard deviation away. And that's on one side of the curve. So if we did both sides of the curve, we would double that. Okay? Within 0.45 of a standard deviation on either curve, it would be double this. Okay, looking at this is between 2 standard deviations and 0. Okay, this one's on the table. So we've got 2.02. This is exactly the book one is actually letting us do this without any math. Value of 4.783. If we look right here, value of 4.783, and there's some extra. I actually did these calculations with Excel. I'll show you that in a second.
So just to be clear, the number 0.97831, that 0.5, that's just the number you use by looking up, you find it by.
Yes. So you can look at it on the chart, but the across the different charts are different. So the one in your book actually just tells you this answer. You don't even have to. Because the one in your book actually is going from 0 out to the 0. Whereas this one right here, 0.478, this chart right here, 2.02, we go to 2.02 right here of 0.222, right? And so in that case, with the value of 0.22, we could subtract that from 1 and we get this value. And then we would get that value if we looked at half. 2.02. 0.217. Let's look at that value. 0.217. Type that in right here? No, one more 0 in front. Okay. So if I take 1 minus this value equals 1 minus this value, I get that value, 0.983. That's this value right here. 0.978. 978. Yeah.
Can you say that again? So the table in the book goes from 0 to Z. Okay, and then the chart on the PowerPoint is going from to the tail
Yes.
of the curve. Okay.
Exactly. So it looks a little like this isn't the case, but really you only have half of the distribution. So this is going from 0 to Z. One of the books is going from Z to the tail. You could think about it as this tail or this tail, but because they're symmetric. The tail going in either direction. It's just this. The book is just 0.5 minus the one on the slide. And this, I found that this one's actually much more common. So I showed it to you, not to confuse you, but you know, you got out of this class and you looked at a different book and a different, in a different book, or if you looked up, you're much more likely to encounter this table. And all this table is minus the values in that table.
You just have to pay attention to what the question.
Yep. And then further, yeah, I'll just skip this for now. Another thing is that, as you can imagine, now with the advent of modern computers, the calculation of z-scores and probabilities is actually something that can be stored inside the computer's brain. So Excel has the ability to do that. So do other software programs, but I'll show you that. So actually, let's the exact same question was asked. This one up here, actually. Let's go with this one. Okay. So here we've got a mean of 75.89. 75.89. That's our mean. Okay. And then the standard deviation is 15.63. Let's call this the mean. Let's call this the standard deviation. All right. So that's the mean. That's the standard deviation. And we want to ask the question, what is the probability of a year that has a frost, the last day of after April 1st, after the 91st day of the year. So let's this the 91st, and we'll call this X. So we want to know what that probability is. Well, in Excel, you can use a function called normal.dist. And what you do is you feed it X, mean, and you feed it the standard deviation, and you have to tell if you want the cumulative. For today's class, that's what you want. We didn't talk about the other value. That's true. So you feed it X, then you feed it the mean, then you feed the standard deviation, and then you just write true here because you want the distribution function. Then you press enter when you're done, and you'll get that value 0.83316. Now what value is this? Because this is an even different value. What value do you suppose that is right there? Now remember, we got the answer. Our final answer down here, 0.1660. Okay, that was our answer. I'll give you a hint. We don't have to look at a z table at all. Okay, we don't have any z values. This is actually a value. Okay, it's probability. So how is that probability related to the value that we got? Oops. Yeah. It's there. It's a slightly different value, 0.1660. It's almost exactly the same value, but we had to round a little bit here because the exact value wasn't there. The table doesn't have every single possible value. In Excel's brain, it has everything, so the values are slightly different. This is, this is a percentage. That's 100th of a percent. I mean, well, sorry, it's of a percentage off or different. Okay, so it's really very close. And in fact, did I type in all the numbers exactly right? 15.63, 75.89. Yeah, I did. 91. All right. So that is the value. Either one of them are acceptable, but know that it always gives you from the start, from the left tail all the way up to your number. So sometimes if you need to figure out, something like this, where we're going in between 0 and another number, we'll need to figure out, you need to figure out both of them and subtract one from the other. We can right now, let's say, what's the probability of frost being after the let's say, what's the probability of it being after the mean? Well, let's just say, no, let's not say the mean. Let's say the 70th day. Slow this down. Okay. All right. So let's think about this. What does this number represent? It doesn't represent the probability of the frost occurring after the 90. It actually represents the probability of the frost occurring before the 91st day. Okay? Line represents the probability of the frost occurring before the 70th day. So what if I wanted to find out the probability of occurring between the 70th day and the 91st day? How do I figure that out?
Would you just subtract those two values?
Yeah, you can. Absolutely. That's what I'm. So take this value minus this value, because what we're doing is, I'm going to draw a really bad drawing. Oh boy. Okay. This is the mean. The means, picture that these look exactly the same. So what we did was, here's the 91st day, and out all of this, the area under the curve, 70th day, and we figured out the area under the curve. And what we want is just the area from the 70th area right there. And so we can subtract out from all of it, and we get just the value, and that's what this is right here.
Well, you said that it's like find the amount of days before 91. How would you find the amount of days like after, like over 91?
Right, so that's what the question actually asked originally, right? This question is looking at the days after 91. Okay, now this is a good question. Say that we figure out the probability of the days after 91, the answer to the other question. After 91 is simply 1 less this. Oops. So it's 0.1668. It's a little bit different than the table, but that's because the table you're single possible value.
And again, the number of days before 91 is just 0.833.
The number of days before 91?
Yeah.
Yes. This is the number of days before 91.
And you get after
Right, 1 minus that number, which would be this right here. And this is the probability between 470. So this is the probability between 70 and 1, if you had to ask that question. Okay. See if there's anything else to cover. All right. So we did the fair bit of is the same thing. Okay, so you could also calculate D now yourself. So this is between negative 2.1 standard deviation and 1 standard deviations. Now we also got the opposite type of questions that we can answer. So here we're saying, what is the z-value when the probability is equal to 25% on a normal distribution? So probability of 25%, what's the z-value that corresponds with that? Well, we can look back in our table. And how would we find that? The probability of 5%. Do you all see that in the table anywhere? Or you can look in the table in your book. In the table in your book, you have to do some math before you look at the table. Because we're trying to find the area under the equal to 25%. We're trying to find the z to the tail. So it actually, you don't, because 0.25, what's 0.5 minus 0.25? Yeah, so you don't have to do any math, sorry. But your value was different. Okay. All right, so you see 2.5 in the book anywhere. So what's the value closest to 2.5? There's actually, I mean, again, we can't find the because it's actually between two values. So we could hypothesize that it's, let's see, 0.25. I see a 0.2486 and a 0.271. So it's somewhere between 0.7 and 0.08. Or if I look on this one, find 0.25 because it's going to be hopefully really close to the same number. 0.2125. Okay, it's between these two numbers. Okay, so it's somewhere between 0.7 and 0.8. Okay, is the z-score for that value. Now, when I figured it out here, I got a value of 0.6745. Okay, I'll show you. You can do this in Excel as well. Actually, you can't do it with Excel because we don't know this. We don't know what the means in this. So it works with the when you know the means and the standard deviations. But let's just say. Let's go out this side. And let's figure out with this distribution what the critical x is. That's 25. In other words, 4. We would expect to see this happen. Okay? What we can do there is say equals, and it's actually called normal inverse. Now it's kind of tricky. You might think that inverse means 1 minus. I think that you could figure out the 1 minus part on your own. They don't need a special formula for it. Okay. Inverse here actually means that we're trying to find the value, and the other one that we did before, probability. So you're either trying to find the critical value or you're trying to find the probability. Fine. Okay. normal dist finds the probability. Normal inverse returns the. Okay, it doesn't say that, but that's what it does. So if we click it, see, you give it the probability 0.25. You give it mean, and you give it the standard deviation, and what it does is it finds that critical value. Now, what's interesting is that it's doing the same thing where it's starting on the left of the distribution and going up. Okay, so you still have to do some math in your head. What do you interpret this? Like what that value is the last day of last. Okay, but what is 60? Another way of saying 65. I don't expect you to know what calendar it is because I don't really know. I guess we could figure it out just based on this other information, right? So 76 is March 17th. 11 days before March 17th, which would be March 6th, right? So it's March 6th. So what is 6th? That's what I'm trying to ask. Based this formula right, what's March 6th mean?
There's a 5% probability the last frost will be after March 6th.
Okay, almost.
There's a
Remember, it's going.
there's a 75% probability.
No, it's 60. Oh, sorry. But there's a 75%. You're right about that. Okay. You could say it a few different ways. But what Ashley just said is there's a 75% probability that it will occur after March 5th, 6th, and that's true. Okay, she's right. Another way to say that is 25% chance that it will occur before March 6th. So remember, in Excel, the way Excel, it's always from the left to the right. So what if we wanted to change this? What we're trying to ask is, what is the latest it will freeze 25% of the time? The latest it will freeze 25% of the time. The latest that it will freeze 25% of the time. Or sorry. No, I guess the latest it will freeze 25% of the time is that. The latest, what I'm trying to ask is, yeah. I guess if you ask it right, then you can do it. The latest it'll freeze 10% of the time is what I was looking for. I found the way to say it with the 25%. I guess it'll freeze that day or later 25% of the time. Well, that's what I'm getting at. The answer there is 7. So this is saying that it will freeze on this day, whatever that is, 86, the 86th day. It'll freeze on that day or later 20% of the time. And to answer that question, you need to feed that formula because it's looking the area beyond that value. All right.
Another example with that one was the invert.
With the okay. Let's see if there's another. Well, we could. We could come up with some of our. Let's see if there is another example. The mean and the standard deviation for this formula here, the degree day. So let's write that. 4, 6, 9 is the mean. Standard deviation is 370. So the X. So if the mean is 4695, which is the heating degree number, we have a value of 370 as the standard deviation. Let's find out what the probability is that we will need 5,000 heating degree days that year, more energy. What's the probability of 5,000 or more heating degree days? Okay. This is another example, and it's actually going to be what probability level do we want to assess? Let's say, oh, we're actually trying to figure this out. That's this side, sorry. So if we want to figure out what the probability is that we're getting to 5,000, we'd go like this. Normal distribution, and we'll feed it the X, the mean, the standard deviation, and we say true. Oops. I gotta spell true, right? And we get a value of 9.51. So, in other words, 5,000 is, let's look back here. Don't pay attention to these numbers. Actually, this is in 5 is up here somewhere, and we just got a value, and that value is the area under the curve. Okay? If we're trying to ask the question, what's the probability of getting a degree day that's 5,000 or greater, number of degree days required, it's 5,000 or greater, what do we have to do? I just figured out to get the rest of this. 1 minus. Exactly. And so we take this number, and we say minus this number, and that's the probability. So for this particular area, there will be 25% chance that in any given year, the amount of degree days required for that area will be greater than 5,000. Conversely, there's an 80% chance that the number of degree days for that year will be less than 5,000. All right. Now, if we wanted to figure this out manually, we would just numbers into the z-score formula. Remember the z-score formula was the value minus the mean divided by the standard deviation. So that's the z-score value, 0.82, but that's in what units? Yes, that's in standard deviations. So that's what we have to go to the table for, and we would get 0.82. We get a value of 0.2939, the value would get, and that value is actually from 0 to the z-score. If we want to figure out, if we want to figure out the tail, we have to say 0.5 minus this value, and we get a number that's pretty close. Okay, it's not going to be because the z table isn't exact, because I guess what I'm trying to say is look at that number, and the z table is out to the hundredths. See? Out to the hundredths. We don't have the 4 part. And so that's why this number and this number, but you'd expect in the thousands that they wouldn't be exactly the same. We didn't provide a number here out to the thousands. We provided a number out to the hundredths. And so out to the thousands, they're different. That's what I was trying to explain earlier. Okay. So that's doing it, the way we taught in the book, and Excel figures it out because it's got all the tables in its brain. Right? Okay. not in its brain, in its memory. Okay. One more thing, though. Let's do another example of the opposite type. Okay. So here is the mean degree days, standard deviation of the mean degree days, and we ask the question, what is the extreme degree day that I'm only going to encounter 1 year out? I'm only going to encounter this 1 year out of 20. Okay, how out that value? I'm going to know is the area of the curve at the extreme upper end or greater. What is that? 1 year out of 20. What's another way to say that in probability? 0.05, right? So I'm going to use the normal inverse, and I'm going to feed it 0.05. How am I going to feed it 0.05? Right when I do this, because I'm asking up on the extreme top curve, what's that probability that's out there? 0.05 because what I'm going to do is get this side of the curve, but it's the same thing as that side of the curve. And then the mean is this, and the standard deviation is this. Okay. Value, actually, yeah, I'm not figuring out the area under the curve. I've got the area under the curve. What did I do wrong? Well, I was right when I started. I need to say 0.95 because I'm trying to find out how many degree days I will need or more 1 year out of 20 in those very unusual years. So 1 year out of 20, it'll need to exceed 5,303. 1 minus 0.5. Because I'm trying to figure out this, and so I need to feed it. Because the thing is expecting what's this area, and I'm trying to find the critical value. And if I 0.05, I'm going to get the critical value down here. And if I feed it 0.05, I'm going to get the critical value up here. Okay. So another thing is to pay attention, because almost the number, if you get an answer and you're like, just look at the answer and see, does it make sense? Because if that's what I did, when I got 4086, I could compare that to the mean and think, well, that's not really what I wanted. I wanted that on the other end, because this number is way down on this end. It's much mean. And so then I said, that's the problem. And I just fixed it. Okay. Now we could also solve this exact same thing using the tables. We would do that is we would this sort of math right here. We would take the mean. So let's see how close we would get. So that we're going to take the mean value, and we're going to add. Whoops. We're going to take the mean value, and we're going to add 1.28. It's not going to be 1.2. Figure out where it is on the z-score, but we're going to multiply that by this value times. So we need to figure out what the z-score is for that value up there. If we look at the table here, it's actually 0.0 in the book. 0.05 minus 0.5. 0.45. So 0.45, we get a value of 0.1736. Actually, did I do that right? No, I'm looking at the z-score. So yeah, I'm looking for a value of 0.45. So that is 0.4. See how there's a point. 0.4. There's a 0.4495554505. So somewhere between 0.4 and 0.05. Let's just split the difference and say 0.045. 0.045. Do something wrong. Oh no, it's sorry. It's 1.65. Okay. All right. I did something wrong. 1.645. Yep. See, it's almost exactly the same because I estimated. All right. Anybody totally lost on how I got 1.645 on there? Or you guys got that?
Where does the 1
Okay. Yeah. The part where I was in the. Okay, so we already established that we need out this critical value, right? And but we have 0.05. Okay, right? The book. Look in the book, and it looks like looking from 0 to the z-value. We're trying to find the z-value. We don't know what the z-value is. So we need to find the stuff in the guts of the table. That's what we need. And we don't need to find 0.5. That's the tail. And this is actually showing us that we need the value from z out to z. So to get that, we take 0.5 and subtract 0.05, which is, okay? And what's that? What's 0.5 minus 0.05? 0.45. I said, I looked in the table for 0.45, found it. It's on the line that says 1.6. I first ignored that by accident, and I just looked at, it's between 0.4 and 0.5, but I forgot I had to add 1.6. That's where I messed up. So it's 1.64, and then I just kind of added halfway between 0.45. That makes sense? Got it up? Good. So that is how I got that value. I got the z-score. So instead of 1.28, the z-score 1.28, I plugged in 1.645, and that's how I got the critical X value of 5303.6, which is really close. Check in the value that was absolutely closest, which some people will do. Looks like they're exactly in between, so probably why it was so good. But somebody might stick one of the other values in, and you can by 3 degree days in that case. All right. So when you do the homework, take into account that depending on whether you're using Excel's or whether you're using this table or some other table, typically you're only going to have 2 significant digits, and so your answer will be fine within 2 digits. All right. Okay, so I was looking for some other examples of things that we could do from geography. So I Googled. Unfortunately, the book author has that example of the last day of frost, but unfortunately he doesn't provide any other, even in his data, which I put. No, I've got it. Let me just show you what I mean. The last day of spring frost. Here. So his data, here's the last day of spring frost. Open up his data. he only the average last day of spring frost. Okay? So there's no standard deviation. So we can't out for every single day. We only have Waycross Georgia standard deviation. So we can't figure out what the values were. Now we could, because he cites the source as being the National Weather Service. So somewhere in there, or maybe it was climate data, I forgot. Somewhere there is probably a table that shows the last, data that shows the last day of frost back, 100 years or much recording, maybe back to the 50s, so maybe 50 years. The last day of frost. So we can calculate the mean and standard deviation. Okay? All right? But the book data doesn't have that. It does have it for the heating degree days, so we'll play around with that in a second. First, what I did was I actually Googled the last day of frost. So I got a table. I know we're not, but I got a table of all of the North Carolina weather that are public that have been recording since 1951. So it's not. And it gave me the average date and the standard deviation for the last day of frost for that station. So, Cherokee's up in the mountains, where I went and watched the eclipse last semester in that area, and there. Their average last day of frost is they got a standard deviation of 11 days. So up in the mountains, but there's lots of variability. Let's look and see is there like a, yeah, Morehead City. Anybody know what it is? New Bern. These are both, Morehead City and New Bern are both down on the coastal plain area. Okay? So both of those, interestingly, New Bern and Morehead, they're both in late March 20th, March 22nd. So we're well over a month before the mountains Cherokee experienced its last day. And they've got pretty close variability, but actually a little bit more variability, particularly in city one. All right. Okay, so say that we wanted to make a map of the of any particular time. Like, let's say we want to make a map of what would be the last day of frost. 95% of the time, the last day of frost would be this or earlier. So, like, if you really wanted to be sure, almost every year, in other words, only 1 year out of 20 will be wrong. The last day of frost is going to be this day or later. We could do that. The easiest way to do it would be in something like Excel, or I would probably code it up in Python, which I can show you. But so let's look at this. So I imported this into Excel. Okay. Imported. This is the name of the station. This is the name of the. This is the date. All right. This is the. This is the standard deviation. Right? I think that's the date. That's the standard deviation. I have something on. There we go. So the first thing I do is show. I'll just do this again. So Excel does have a formula equals. It has a formula of days, and it will tell you the number between 2 days. Number of days between 2 days. When I pasted this into Excel, all I did was cut and paste it right off the internet. When I pasted it into Excel, it assumed that these dates, 8th of April, 4th of were all, and I'll show you here. It assumed that all those dates, 2018, really isn't a problem. Because 2018, do we have a leap year this year? No. So it's a typical year without a leap year. I know there's some leap years somewhere. So it's a typical day without a leap year. And so if I want to figure out what day of the year April 8th is, all I need to do is use this formula, days, and subtract it from the from January 1st. Date first though, actually. End date, comma, start date. And I press enter. Those are the same exact formula issue. Yeah. Yes, there we go. So I just need to make sure it's a number. I did that. So because I inserted a new, assume that was a date too. So that's the 97th day. You know, that's 97 days after January 1st. And then I just filled this down, and I got all these numbers. And since days are integer values, I got rid of the decimal points. Okay. I'm just going to delete this entire column again because I don't need it. I'm going to make these like black. Okay. All right. So let's say I want to make a map of this, but I want the 90%. I'm going to put some headers on here. County, last frost. I'm going to call this Julian Frost, and I'm going to call this standard DVA, standard dev last frost. Okay. So then what I can do is find out what the percentile, what day it was. Okay. All right, so how would I do that? How would I find out what the date would be that the last frost would be that day or later, or earlier, sorry, that day or earlier, 90%. Or another way to look at that is only 5% would that day be, would the last day of frost day. Okay? So how would I do that for one? And I could look it up on here. And if I did it here, under the table and find the one that was 0.05, which we already would be 1.645, and then I could take that z-score. I could plug it into the formula, so that would be the mean plus 1.645 times standard deviation. Is that the right formula? Let me see. I'm looking at the formula to find the critical z value. Yep, mean z value. Yep. So to hit that, and I can just fill that down because it always the same value. I'm looking for the 95% for there, right? So these days that I would expect the frost to occur not later than that day, almost all the time. 1 year out of 20, it'll occur, but yeah. So it's the exact same one we just figured out, the 645. So I took 95, I took 95, and that 90 total area under here. And really, I just want this area here, which would be 0.45. The whole area is 95. I subtract 50%. I subtract 0.5. I get 0.5. Then I look on the formula. I look for, there's no points on this table, but I look for 0.45. Find it best under 1.645. Did I use 1.645? Yeah, 1.645. Okay. Alternatively, to use a z-table, I could just use the normal distribution inverse, and the problem is 0.95. What would it be? Yeah, because that day that's way out there, that's extreme. I get last frost mean and the last frost standard deviation. I press enter, and then I fill down. So not having to look at a table, I just use Excel's, and the values are really, really similar. Okay. So this is the same thing. Now, what if I put that back into a? Let's see if it'll work. Into a date. I don't know if it will. Equals and statistics anyway. Days between two dates. Returns the day of the month. I wonder if I go like this. This plus. I'm mad if I don't tell it it's an int. And then convert this into a date. And I don't want to report the year as a general. Okay, so the 22nd of April. So the table is easier to read. And then I could go ahead and fill this guy down. So, in Cherokee, the standard deviation was 11. I'm going 141 days out to the 22nd of May. That's like, most of the time, that's the last day I should expect to see a Cherokee up in the mountains. But also Transylvania's up in the mountains there too. 21st of May. Ooh, 30th of May. I wonder where that is. Macon. Oh, that sounds like mountains too. See where that is. It's up in the mountains as well. Okay, so that makes sense, because that one was the 30th. And one of the reasons why it went so late is the standard is 14. See that? Even though Cherokee was the 4th of May, which was actually earlier of May, the standard deviation was 11. I'm looking at this line and this line. Okay, so the actual date of the average last frost day is earlier in Cherokee than Macon. However, over the time period, which is the last 60 years or so, the standard deviation has been higher. 14 versus 11. And so, if I want to bet on when the last frost day will occur, 95% of the time, it's going to be a later date because the standard deviation is higher. And then let's look at some of those, well, I said New Bern, right?
So if we want to find the critical X value, in this example is day,
Yeah.
then we can manipulate the Z and solve for it. Or we can use normal.m.
Right.
And then if we want to find value given a probability, that's when we use normal.dist. No. Or a mean and a standard
Yeah.
deviation.
Yep.
Normal distribution gives us probability.
Yep. So that would be exactly the way to restate it. So what Ashley's saying here is, let's just say we had a data we're really concerned about. Maybe. Let's see if how do we write? May is the 5th month. 5/1/2018. Okay. So that's, and I want to know what the probability is of I want to know what the probability of location that frosting will be over by May 1st. Then I could do normal.dist. The reason normal.dist is it's telling you the distance away. So we got the mean, which would be last May. Oh wait. Convert the 1st of May to another. Sorry. What's 4 minus 3 would be 120. So actually, let's just change this to 100. Format cell number. Okay, so this is the 1st of May. Format cells. Actually, we don't have a column because it's always going to be 120. So let's just delete it. And we're going to figure out the prob after the 20th, the 1st of May. 1st of May. Okay, so the probability would equal the normal distribution. X is always going to be 120 in our case. The mean is going to be this. Sorry, that. And the standard deviation is this. The cumulative is 2. Get to format cells to a. Okay. So yeah, it's telling me the cumulative distribution point, so that's actually what I want. So I don't need to do any 1 minus. So these saying is in Stanley, the average last frost is on the day. So what's the probability it's going to be on the 120th day? It's 99%. It's almost always going to be after that. Whereas in Cherokee, the 120th day is only the last day of frost, about 40% of and 23% in Avery, 10% in Yancey. Okay. So we've got those that's looking at both ways. Okay.
Then before May 1st, we just subtract out from one.
Yes, the probability that occurred before May 1st. No, sorry. Probability that it happens before May 1st.
Okay, so after
May
May
1st.
1st.
That one. Yeah. So the probability that occurs after May 1st is you'd only expect to see that 1% in Stanley, North Carolina. Which I don't know where it is. Wow, that's, I mean, it's, but it's in the Piedmont. So, it's pretty far south, but still. But where it's like 1, I mean, there's lots of areas where it's 1. So we could change that anywhere, that 120, we could change that to any other day. A lot of these are over 1. Okay, so the point in showing you all this is that if you look at the last figure in the book, you could use that to make a map. So in this chapter, which is on page 100, they've made a map with isolines on it, and got that. But I wanted to reproduce that map, but I can't. They didn't include, the book author didn't include the location in the data. We could pretend. Let's do that really quick. We're going to do that with 2, just to show you how to make maps. But first, I'll do it with the late frost data. Okay. Got my late frost data right here, but see, I only have the average last day of the spring frost. Okay. So they've got the likelihood of it occurring after April 1st, which is kind of similar to what we just did, but May 1st. So what if we wanted to manipulate this table and create a new field? Field had that value in it. Well, it'd be really to do. We have to take it out of here first. Let's just do it real quick. So I'm going to say File, Open, and open that cell. I put it in. C. Six, and then I put it in a chapter. And I could get the DBF file, because DBF files can be read in Excel. You have to be careful of reading a DBF file in Excel is that you don't any of the other columns, and when you add your column, when you add your column, you have to follow the conventions for naming. Longer than, I think, 13 characters. So I want to figure out the probability April 1. So what is April 1? Already, the Julian date for that was already listed. So April 1 was 91. So I want to figure out the probability of that. And so doing, I could say equals 91 there. So the z-score is 0.07. It's already in your book. Okay. Now, what we have to do is figure out the z-score for every single one, though. Okay. Use that formula that already exists in Excel, which is easier to do each one individually. So that's where the Excel excels, I guess. All right. So we need to figure that out. So 90. So that's using the normal inverse, and our probability that we don't want probability. We want the other normal. And the x that we want is 91. The mean is right here. Now we don't have a standard deviation. So what I'm going to do is assume that all deviation values are the same, which would be 15.63. That would be more ideal, much more ideal. I have a column here that had standard deviation, but since we don't have that, this is valid. I'm just saying this is how you would do it. That's why I got the data in Carolina, because it actually had that value. Okay. Okay, so the 91, because I'm trying to recreate the book author's map on page 6.9. I mean, figure on page 100. Trying to recreate that. So I need to figure out what probability of the last day of frost being occurring on or after April 1st. So I'm using one because that's April 1st in calendar days, and C2 is the mean. C2 is the mean. The standard should also be provided in the table. If you wanted to do this right, the standard deviation should be provided. I'm using the standard deviation that I know, and the one for Waycross, Georgia. But to do this, you know the standard deviation of all the locations, right? And that. Now, what I'm going to get here, is it actually what I want? Let's think about it for a second, because I'm going to get the probability under the curve all the way to 91, which is above the mean. Is that what I want? On or May 1st? Do I actually want that, or do I want some other value? Because this is giving me, let's go back to this one. This is giving me, I'm not trying to find the critical value. I've got 91, and I'm trying to find this probability. So what I'm getting is using the Excel formula, I'm trying to figure out this probability, and I'm getting this. So what do I need to do to change the formula to get the right value? Right there. What can I do to change that formula? Because I'm going to get everything but the tail, and I want just the tail.
It's going to be 1 minus 1.
Yep, exactly. So now I've got these numbers here. Fill those down. And I've got all the numbers that I need. These are the probabilities. And he's on the book authors, there's 3 of them, have expressed it in as a percentage. So I could go here and say percentage, and I don't want any decimal places. Okay. So those are the numbers. Actually, it'll be easier to map something different. I'm going to change it back to numbers and decimal places, but I'm going to change this. I'm just going to multiply and do the math. But if I do the math over there, I'm going to do the math right there. No, I got to do that first. This is a case where you need to use your parentheses. So it'll do first, then there we go. That's the right number. So just so that as a percent, so that it'll be displayed the same. Now at this point, I can just hit save, and it will save the DBF file, so I can bring it back up in ArcGIS. I hit save. A warning that it's not actually going to save the formula. So I say OK. It's telling me that I'm trying to save over something. So just for now, because I brought it up, and this often happens, and I bring it up on ArcGIS, it like gets greedy with it. So I'm going to close ArcGIS quick. I don't need to save it. And then I'm going to try to save it again. Maybe these files are read-only, because I pulled them off of a CD. There we go. So save files. What I'm going to do is manually force this to. So I'm going to go to DBF. Base. It won't even let me save this file. I guess that formula is not supported anymore. Yeah, that's the next thing I'm going to do. I'm going to save this as a CSV called last.csv. Okay, I saved CSV. Now I'm going to close it. Probably shouldn't have closed it actually, because CSV I didn't need to close it because I don't. ArcGIS can just. Now ArcGIS doesn't like the extension CSV. Oh, it's right there. That's the save over. So that one's probably still read only. Okay, I probably could have saved it. Okay, but this will work too. Like the extension CSV, so you change it to a TXT. It'll use it. Okay, so now I'm back in ArcGIS, and I'm going to add the last frost data, and then I'm also going to add the last frost data, the TXT data. Okay, and for those of you who do GIS stuff, what do I have to do to get the last data into other data? How do I get this frost? What's the method? Maybe I could join a table. So I'm going to join the frost text data using this SID, which stands for because those values will be the same in both tables. It's going to be together, and all the information from both tables will be in the output table. So now when I look at the frost table, it's got, first of all, it's got 2 of every other information, which is kind of annoying. But it does have this probability after April 1st, right there. Probability that occurs after is the last day. Okay. And then I could, there's a few different ways to a surface with that data. One of the like quick and dirty ways under customizations, 3D analyst, it's already on. Customize toolbars, 3D analyst. So one way to think about this surface is it's a 3D surface. And so I could well, let's do the normal way. So I've got Spatial Analyst turned on, and simply go under Spatial Analyst Tools and do interpolation. I'll just do for now, and I'm just going to leave the defaults. isn't a spatial interpolation class. And I'll leave else. And the field that I want to use, though, is the probability field, which is the last field, this one. So now it's going to use that to build a surface. Okay, it's going to build a surface of probability that the last day is April 1st. And it should look somewhat similar to their table. Interpolation values that they used, what they were. So this is Waycross, Georgia, right there. That point right there is Waycross. So if you go in the book, you'll see that there's this same dip right here, and then it goes back out to this. That city is. Okay, the line isn't exact shape, but some of that's because of the interpolation out we chose. So we made a surface out of this data. But we could use this map to see. But the way you read this is that in these regions, larger regions, there's a 95% chance that the 95 in the very highest, there's an 85 to 95% chance that the last day of frost will be on or after first. Okay? Whereas here, say, 10%. That doesn't seem right, does it? 10% chance. No, that seems right. The 10% chance it'll be on or after. Yeah, it'll be well before that. This is Florida. It's warmer. Okay. So yeah, it's always good to think about it. Sometimes it takes me a few more about things. But one thing that's interesting, I wonder what Conway, South Carolina. It's always warm there. But I wonder how much warmer in Conway than it is in Charlestown, South Carolina. Maybe it had to do with what the station is. Or it may just be there's more variability in Charleston. Who knows? Actually, there isn't more variability because of the way we calculate it. Math is also not perfectly accurate because we didn't have deviation, so we just assumed the standard deviation was the same everywhere. Okay. We could take this map we did have the standard deviations for and make a map of it. It would take a little bit to find out the coordinates for all of these weather stations. And I'm sure that takes more, but I didn't look for it. So we're not going to make a map of this. Okay. So that would be a map of all of these weather stations. It'd be just in North Carolina. We could do an interpolation, and we could figure out a surface that would show us whatever variable. We could map this variable. Okay. We could map this variable, the last day of frost, percent probability of the last day of frost. So that might be more useful for. Okay. We could map this variable, which is the same. We could map this variable, but then show that value on the map. It's more of a clean value. All right. At least on the line, so the ISO lines, we can show that value. Okay. I'm going to turn this off and this off. And turn this on. So one of the things he does do, though, is show he does have this value included in the table. The heating degree days, we do have the standard deviation mean, and in fact, he's already calculated the heating degree day at 10% and at 95%. So this one should be well below the mean. This one should be well above the mean. Well, okay, so he's talking about 95% of it being that day or lower, and that amount or higher. And then he's got the z-score calculated. All right, so if you wanted to, anybody wants one more example, I could take the numbers and calculate this out in Excel again.
From that, you could just run the IDW tool.
Run the IDW tool for either of these two numbers. In fact, it may be interesting to see the z-scores, the one standard deviation, the 10 and the 95 z-score, but these make sense to almost everybody that understood what a heating degree day was. We could make a map of that. Oh, there's another tool for making. So it's got a lot of information in it, but there's another tool for making surfaces, and that's called the geometrical analyst. And allows us to choose the data set and the source. So if we wanted the 10 percentile, which appears to be the very top tail, the top 10%, the probability that a heating degree day will be will exceed this 10% of the time. It'll exceed this 10% of the time is this number. So again, we could accept all the defaults if we wanted to. We talk about this in one of the other, in the spatial analyst class. But this is still looking at IDW, but it gives you other information. It tells you how far off each measurement is from the prediction, but it still produces the same sort of map. Okay, I'm going to move the stations up above it so we can see the stations. So this is saying that a heating degree day will exceed this value here 10% of the time. So in areas that are the darkest red up here in Canada, and the degree day will exceed 8,552. That's a decimal point there. So it's 8,552. It will exceed that 10% of the time. The blue areas, like where I'm from in California, and South Florida, means that it will 2,800, at 10% of the time, at the very extremes of that. It might make more sense to convert this to a
Is there a tool in there that just draws like lines?
yes.
Like a homework task?
Yeah, so there's a tool that does that. That's under, where is it? It's analyst. You got it? I'm going to search for it. I think it's in the 3D analyst. Contour. What's the name of the tool? The contour. It is under 3D analyst for some reason. So if you go under 3D analyst, right here,
probably could have just looked at it.
There it is right there. Contour. So you can contour something. Now, I created this raster in, I created this one right here. I created it in geostatistical, and it's not actually there yet. ArcGIS is just displaying it, like it's creating a line displaying it. In fact, as you zoom in, it recreates it just for the that you're looking at. It's not permanent, and that's why it doesn't show up in the list. See, only this one shows up in the list that I created in Spatial Analyst. If I want to make this permanent, I can just right-click on it and say Data Export to Raster. I'll have it. I have to specify a cell size at that point, and I could just save it out. And one thing that we did do that's really actually bad, I just kind of did this quick and dirty, is that we created a surface from latitude and longitude points. Okay, we shouldn't do that. We should always data before we would do that. Contour this real quick. So we'll do created, and we'll say contour interval of 1,000 degree day, and we'll say OK. And then bottom, so we'll move it up to the top, and we'll get rid of. I'm going to get rid of the city state. So those are the contour lines for that surface. So they're every 1,000. So we could click on one, and we could say that's 31. No, sorry, that's 5,000. That's 4,000. 3,000. That's 2,000. It's probably 2,000 as well. Okay, so that's how we could do that. Now, let's just say that we did that for. Well, let's just do it. Okay, so I'm going to do that for the other one, the last day of fall. The contour interval. I'm going to switch 2 days. Or maybe that's too busy. That's too crazy. I'm going to rerun that. So I can go to geosync, results. I'm just going to rerun it, and 10 days. I think that's what the book did, right? 10, yeah, 10 days. So there's our 10-day. Now what we could do is that in our everything's 90, 80, 70, 60, we could create a new column that represents days, right? Days since January 1st. We could create a column, and we could change that to a nice day. I could say April 9th, January 9th, or whatever days it was. So we could create a new column. Add field, and we could make it tag. We could call it day. Okay. We'd have to calculate what each one was, but let's just say we could make them all May 1st for now. Oh, trying to go too fast. You can put it in quotes. Calculate it. We got May 1st there, and then we could label it. Let's turn off this one because it's that layer with the night. So we have to go into properties and set that to be nice label, not ID, but okay. Now, obviously, all mine are going to say May 1st, but if I, the ones that were 10 days to January 10th, and then the ones 20th, January 20th, the ones that were 30 days would be changed to, February, whatever that would be, and so on. Okay? So that's how I could change all those days. All right. Any other questions?
Yeah, would it possible to build building maps without ArcMap, like just normally?
Yeah. People made ISO maps before ArcMap. The way that you would do that is the way that I would do it. One of the ways we learned in cartography would be to write the value out next to each one. Are you talking?
Yeah.
Okay, yeah. Write the value out by each one, and then approximate a line that was the same. So you'd say, okay, well, if this value right here was 30 and this value right here was 5, then if I wanted to draw, what's a bad name? This one was 20, was 35, then I would draw the 30 line through that. I would try to find where it went.
Yeah, no, I was talking more about the file and like the thing before the contour.
Yeah.
Probability.
Yeah, I mean, well, I did the actual calculation in Excel. I mean, you could do it in Excel, you could do it in, I didn't actually show it, but there are functions here. I was doing it before class. There are functions in Python for calculating. This is the equivalent of norm.dist is norm.cdf in Python. So you give it the x value, you give it the mean, you give it the standard, and you get a probability. And this is the equivalent giving it this is the equivalent of what's the other one? Inverse, yeah. Norm.inverse, norm.ppf. I was just testing it here. I gave it the output of this one. You give it a probability, a mean and a standard deviation, and you get out the critical value. And I was testing to make sure it was the same. And I knew that Python did it. I've coded it before. I remember that it was norm.cdf. I Googled normal and statistics in Python, and I got, it's normal. Yeah, but you have to import this. You have to import this SciPy. Or you can just say import SciPy, and you can say SciPy.norm.cdf. If you're programming in Python. Okay, any other questions? And there's other software packages. R is a statistical open source software package that probably has another similar SAS is kind of like, or sorry, not SAS, SPSS. It's kind of like you wouldn't really want to do that in SPSS because that's more for with raw data. And we'll talk about that later when we deal with more raw. Say we've already calculated the mean and standard deviation. These are ways to get that data faster. All right. Any other questions? Hello. Good. Looks like it's still recording. I'm going to go ahead.